Okay, so I got top of the hour, so I know we've got somebody waiting on a train and somebody's got strep throat. Actually, Cameron has strep throat, so we're glad he's staying home. And so, yes, so we'll just go ahead and get started. So a lot of these first slides are like, oh, we've already talked about that, and so that really works. You can look at today's lab, and it's kind of broken up into sections. The first section is just PowerPoint slides. We'll be kind of flipping back and forth. Kind of the second section are some handouts that I usually give for this lab. And then the third section actually is where you're going to fill in. The third section, to me, begins with, I kind of marked it here. Yeah. I guess I didn't mark that one. It's like on 87, 287. I call it part 1 where it says cations from the metals of group 1A, 2A, 3A. So that's kind of the 3 sections we'll be kind of going back and forth. But again, this should look pretty familiar. Notice the title of this lab is simple compounds and only compounds that are ionic compounds. So what we've talked about is look for the metal and you have an ionic compound. And here's where I get to kind of mix it up a little bit. Okay, we talked about valence shell electrons. They are in the highest N, and you know the number of valence shell electrons for the group A elements is the number of the group. Okay, that's how many valence electrons there are. We also talked then, along those lines, group 1A metals have 1 valence electron, 2A metals have 2 valence electrons, 3A metals have 3 valence electrons. And we talked about how these valence electrons jump ship to make the cations +1, +2, and +3 respectively. We talked about, when we're talking about ionic compounds, it's definitely an issue of of electrons being transferred. Okay, so we said electrons can transfer, electrons can be lost, or electrons can be gained. We said that actually metals tend to lose electrons, nonmetals tend to gain electrons. They form a cation and an anion respectively, and then you get the ionic bond between them. So that's what we're focusing on today. The reason they lose those electrons or gain those electrons is get that complete octet. So in lecture yesterday, we talked about, introduced the term monoatomic, mono meaning 1. So 1 atom ions, monoatomic ions. That's exactly what we've been talking about. Okay. Polyatomic ions, and actually that's in part 3, section 3 in today's lab. We're going to be taking it up a notch. We'll do 3 different kind of sections. Polyatomic ions, for example, it would be nitrate, NO3-. That's an example of a polyatomic ion. Hydroxide, OH-. Most polyatomic ions are negatively charged. They're anions. It's polyatomic because it's more than 1 atom. That's it. And we'll be talking about those. And yes, you do need to memorize a handful of polyatomic ions. Okay, and I have some like little, don't let me forget to give you these little flashcards that you can make and fold over, cut them up if you want. Okay, so the monoatomic ions or the polyatomic ions come in 2 flavors. Cations are basically positively charged because they have a few less electrons than protons. Anions are negatively charged because they have a few more electrons than protons. All right, so this is actually one of your first kind of sheets. This slide is also a sheet in kind of that middle section. So this, you can kind of see what we've been talking about, okay? I told you to put a +1 up here, okay? I told you to put a +2 right there. I told you to put a +3 beginning with aluminum right here, okay? Then I usually start with 7A and go that way, so I told you to put -1 there, a -2, and a -3. So you actually can already kind of see these monoatomic ions, just exactly like we talked about in lecture. Now there are the problem children, okay? I'll go ahead and, of course, what I have in purple there, those are the group B elements, the transition elements. The transition elements, the group B metals, they oftentimes can form more than 1 ionic form. They have more than what we call 1 oxidation state. We picked on iron the other day, and iron forms a +2, and iron also forms a +3. So actually in blue, what I have in blue here, you'll hear me use the phrase, you can hang your hat on it. And I don't know where that came from, that phrase. What I'm trying to say is you for sure know that 1A is going to be plus 1. 2A is going to be plus 2. 3A is going to be a plus 3. You for sure know, again, the halogens are going to be minus 1, 6A minus 2, 5A minus 3. You can hang your hat on it. Because I'm going to contrast that actually in the middle part. I might have said that last section has kind of your worksheets for today. That part 2 for your worksheets, actually, we're going to be looking at those. All right, so again, I think this is a slide we got to yesterday. We actually looked at some electron configurations of the metals when they form cations, and we showed that actually all of their valence electrons took off. Their new valence shell then was the N minus 1. Okay, so we kind of did that, and I think I have that right here. No, I didn't. This actually is a deja vu slide. Sometimes I don't get this far in lecture, so I'm kind of repeating myself. But again, you can hang your hat on the 1A, 2A, and 3A. All right, the nonmetals forming anions, you can hang your hat on 5A being a minus 3, 6A being a minus 2, and 7A being a minus 1, like this. So you don't have to fill in any of these slides, do you? All right, so now we're kind of leading up finally to the first section that I'm going to turn you loose. I only want to, on this first section, we're going to concentrate on things that you can hang your hat on. There he is. This has all been reviewed, so you're fine. Okay, so I said in lecture yesterday that you want to, the two things you are tasked with on your test and in your homework and in this lab are for ionic compounds. You have to make the formula, okay, and you have to name it. So we're going to talk about both aspects of ionic compounds, making the neutral formula and naming it. Okay, so it needs to be neutral, kind of like I showed you yesterday in class. So usually when you're writing it, the formula, now sometimes, especially my intro gen chem students don't get this, but I'm going to hold you guys to task. Do not show the charge, okay? Like for instance, NaCl, okay, that's sodium chloride. We'll talk about the name, but I don't show the charge. I don't show Na plus and Cl minus. They're there, but do not show the charge, okay? Like it says, usually you write the cations. You usually write the metal first, okay? Usually, I suppose there are some exceptions, and the anion last. If you need more than one polyatomic, now remember I gave an example of polyatomic was nitrate, okay? So for instance, if we pick on nitrate, if you're going to combine nitrate with, oh, we need a periodic table in this room. If you're going to combine nitrate with magnesium, okay, I'll show you why this is, but magnesium, nitrate, NO3, honestly, you're going to need 2 of those. So all this is saying is that if you need more than one, which we do in the case of magnesium nitrate, you put nitrate in parentheses and then you put a number outside. No parentheses are used if you only need 1. So an example of nitrate again is sodium nitrate, NaNO3. In both of these cases, actually, I have a neutral formula. We'll talk about that. That's kind of like, it's section 3. So my hint here, I call it crisscrossing, and I think there are other textbooks that do it. I don't know if Petrucci does it. But in order to write that neutral formula, I could tell you, for instance, I could task you with, I want you to combine magnesium and chlorine, okay? And you would go to the periodic table and you'd say, well, magnesium is 2A, okay? And you would say chlorine is 7A, and you would do that. Now, the crisscross method goes like this. Basically, I rewrite the magnesium, and the number of magnesiums I need is the magnitude of the charge on the anion. So the number of cations I need is 1. Okay, crisscross. The number of chlorines I need is 2. Crisscross. Okay. And as it turns out, actually, and I kind of evaluated it this way in lecture yesterday. If we want to see what we have with MgCl2 is the formula of our ionic compound, we'd say I have 1 magnesium. It actually is a +2. I know that because of where it is in the periodic table. We have 2 chlorines, and they are each -1. Okay, that's what I mean by neutral, and crisscross will get you there. There is one catch to crisscross, and I'll try to kind of point that out when we get to it. But it's kind of nice, okay? Kind of easy. These are 2 polyatomic ions. Most polyatomic ions are negatively charged. They're anions. This is carbonate, CO3, 2-. And yes, you're going to have to memorize that I have to know the name for carbonate. You have to know the 4 atoms that go together to make carbonate, and you need to know the charge. Okay. But there are just a couple of positively charged polyatomic cations. So here's a polyatomic cation. This is actually, remember I whined about it the other day. The neutral molecule we deal a lot with in general chemistry is ammonium. Okay, ammonia, I said that wrong. The molecule's ammonia ends in IA, but this actually is ammonium. So, like, really? Could you not name it something else? NH4+. But let's go ahead and crisscross. I'll just kind of do it up and where it is. So if we crisscross, do you see that the number of NH4s we need is 2? Okay, crisscross. The number of CO3s we need is 1. So that's kind of how that goes. All right. Whew. All right. So that was crisscrossing. That will give you the neutral formula unit. Do not include the charges in your formula. Okay? Do not include the charges in your formula. Now, how do you name it? Well, you give it a first name and a last name. And usually it's written with cation and anion, and that's how you name it. You name the cation, and then you name the anion. Okay? For the first part that we're doing today, for those ones you can hang your hat on, the 1A, 2A, 3A metals, okay, for the metals, the cations that we're going to do first, the monoatomic cations, it's just the name of the element. So if sodium is your metal, it's 1A, you can hang your hat on it. So sodium, it's just going to be plain old sodium. That's going to be the first name. Now, in part 2, when I turn you loose, I'm going to talk about, you can also hang your hat on, and these will be in part 2. You can also hang your hat on 3 group B elements, 3 group B elements. And so this is where sometimes I find them on the periodic table. They make kind of a little L shape. That's it. I just got to have a periodic table. So if you find silver, cadmium, and zinc on your periodic table, well, there's one in here. Those you can always hang your hat on too. And so actually those will all be the name too. So silver is +1 always, cadmium and zinc are always +2. All right. So what about the anions? And I mentioned this the other day. Basically you lop, I think that's a verb, you lop off the end of the non-metal name and you replace it with ID as in dog, E. I feel rude enunciating the D, Id, because as some of you may know, there's an ite that we're going to talk about in part 3, and they are totally different. Id and ite are not the same thing. And when I go to grade stuff, I'm pretty careful about looking for that. You can't BS that one too much for me. I can tell Id and ite. All right. So you probably already have these. These might come in handy. These are just the monoatomic anions. They are the nonmetals, and you know the charges because of the group they're in. So, you know, instead of oxygen, it's oxide. Nitrogen is nitride. Sulfur is sulfide. Chlorine is chloride. Hydrogen is hydride. Bromine is bromide. Phosphorus is phosphide. Fluorine is fluoride, and iodine is iodide. All right, part 1 worksheets. So I'm going to do the first one. I kind of told you we're going to stick as a group, which we are, but I'll show you the first one, what I'm after. and then this kind of the second part, what I'm after, and then turn you loose. So this would be on page 287. So let's pick E, okay? In each case, I want you to write two things. And so for E, for instance, it looks like this. Mg2+, these are the component ions. P3-, okay? So the first thing I want you to do is make the neutral formula unit. I like to crisscross. So it's looking like this. The number of magnesiums I need is 3. The number of phosphoruses I need is 2. QED. And then the next thing, the last thing I want you to do with that line is write the name. So since magnesium is a 2A metal, it's just going to be magnesium. Now, I'm not a good speller, but I can tell the difference between magnesium and manganese. So magnesium, and then the last name, it's not phosphorus, it's phosphide. So that's what you'll do for all that top section. And then you can go ahead and do the bottom section for part 1. And the bottom section, I give you the name and ask you to give me the component ions and then the neutral formula. So let's pick on F. F on the bottom part, and that's aluminum sulfide. Okay, so aluminum is 3A, so the component ion is +3. Sulfide, of course, comes from sulfur. Sulfur is a 6A, I think, and so it would be a -2. So the last thing I need you to do is to write the component ions, or sorry, these are the component ions. The last thing I need you to do is to write the neutral formula unit. Now, if you ever have to go from a name like this, which you will on your homework and on the test, from a name like this all the way to the formula, neutral formula unit, I would go through the component ions, because then you can crisscross and you kind of get your bearings. Okay, so the number of aluminums I need are 2. The number of sulfurs I need are 3. I don't have to think too hard if I crisscross. So like I said, I'm going to kind of, I'll give you just a little bit to kind of start hashing those out and kind of meet you on the other side. What I'm going to do, I need to go print them off, but actually I'm going to give you an answer key to the stuff you're doing, the 3 parts, so you can actually check your own work. Especially that last part, though, with the polyatomic ions that we're going to get to the third part, I'd kind of like to see your stuff before you leave. But let's look at the next part. So the next part, it's kind of a smaller section, and all it does is focus on kind of these ones that you cannot hang your hat on. Notice, actually, you cannot hang your hat on group, I guess it would be group 4A metals. Why? Because like SN, of course, SN is tin, and notice we see that tin has 2 cationic forms, okay? And we did say that you can hang your hat on 3 transition elements, and this is where I was kind of trying to tell you they make kind of like a backwards L. I don't know. So zinc and cadmium are both +2 always, and silver is a +1. Now I know that there's kind of some blanks here, and they could be filled in, but I didn't choose to fill them in. Okay, so the thing comes in the metals, the cations, the ones that form more than one cation form, like iron is a +2 and iron is a +3. When we go to name that thing, what we need to do is incorporate in the name, not in the formula because that's like normal, but in the name we need to say what charge it is, which cationic form it is. There are actually 2 options, and we're going to go with this one, the Roman numeral, okay? The Roman numeral in parentheses. So for instance, if it's Fe3+, okay, the name is actually going to be iron 3. Sounds like a movie. Anyway. Okay, that's what I mean. Okay, so anything that, this is where I try to kind of, I have hard time explaining it, but you're going to hear me say anything that I'm drawing a purple around, Let's see, that's not purple. Anything that I'm drawing purple around, okay, those you do not need Roman numerals. You do not need Roman numerals. You do not need Roman numerals. Let me find my little L here. No Roman numerals. No Roman numerals. Everything else, yes. Everything else, yes. And the problem is when I go to grade these, if you use Roman numerals, you're not supposed to, you get it wrong. And if you don't use Roman numerals for the cation, and you're supposed to, you get it wrong. So, grr, right? Okay, so this actually, the purple is up there. Okay, purple's up there. Do not use Roman numerals. When the cation comes from 1A, 2A, or 3A metals, do not use Roman numerals when it's silver, zinc, or cadmium. Do not use Roman numerals. You must use Roman numerals for all other metals. That would be metals then from the 4A or 5A and the group B elements, group B metals. You got to use Roman numerals. And even if there's like, you're like, well, Mrs. Snipes, looks like there's only one cationic form of it. Do I need to use Roman numerals? If it's not 1A, 2A, 3A, nor is it zinc, cadmium, or silver, yes. Okay, there you go. So we're going to use Roman numerals, but actually some of you may have learned, and sometimes I'll have students in here, so we're going to use these, okay, that correspond to these. Sometimes I have students that actually know their other name. A lot of times if you pull up an old-timey bottle in the stockroom, it'll say, for instance, ferrous chloride. And ferrous corresponds to iron plus 2, okay. What I would do is call it iron 2 chloride, okay, instead of ferrous chloride. So if you're one of those, we'll work with it, okay? But so these are, you can see the corresponding. This is what you would, how you would name it, okay? And I hesitate to even say this because over the years, what I've seen students confused with is they want to use Roman numerals for the number of cations that you need in that particular to make that compound. No, the Roman numerals go with the charge, okay? The Roman numerals go with the charge. Crisscross goes into how many you need of that type, okay? So sometimes it's kind of a reverse crisscross to know what sort of charge it is. So these are just some more. All right. Okay, so seems like we already did this one. Is this the slide too? So you're ready for part 2. So let's look at an example. Actually, I'm going to show you in this one, I'm going to pick one where the crisscross method gets you almost there, okay? So this would be in part 2. The first part, of course, you need to, yeah, let's look at G. And that's an example of where the crisscross method doesn't entirely get you the neutral formula. If we pick on G on the top part, we're supposed to, our component ions are given, Fe3+, okay, and O2-. Of course, we know that the, what's that?
That's F.
Oh, S2-, thank you. We know that the sulfur is 2-.
Oh, but the first, sorry.
Oh, that's not, okay, thank you. I was crossing my things. I wanted to do one that was, okay. G, pay attention, Snipes. Okay. Look, Pb 2+, how's that? All right, good. And the other, the anion is S2-. So what I started to say is we know that sulfur is 2-. The lead, it could be kind of an assortment of things, but we know this is a 2+ one. If you take those component ions and crisscross, you'll notice that the number of Pb's I need are 2, okay, and the number of sulfurs I need, or sulfides I need, are also 2. Now, way back, it wasn't that long ago, we talked about chemical formulas, and we said actually for ionic compounds, I think we said this, usually the formula is given as the empirical formula. And do you remember how empirical formulas worked? Okay, empirical formulas actually, if you can reduce it, you got to reduce it. So actually this can be reduced is my point. So this is not the correct formula. So the correct formula would be simply PBS. Okay? So you kind of have to watch out for that after you crisscross. If you end up with something that you can divide by whole numbers, then you have to do it. So if we name this thing, of course, it would be lead 2, Roman numeral 2, because that came from its charge, and then the last name is sulfide. And I think sulfide can be spelled with F or PH. I think you'll be okay. Now, down there at the bottom, yeah, I think you're okay. I'll just turn you loose. You're fine. So I'll give you a little bit of time to work those. I found the file and it's printed off. I just need to grab it, the answer key for all 3 sections, kind of when you're done. So let's go ahead and I'll show you what I need to tell you about the last section. So what I tell students is if you find, let's see, is it the next one? Oh, no, it's not. You guys, the last PowerPoint slide, okay, if you would go ahead and add these 2, that would be great because I don't think it's on there. Remember that PowerPoint slide is an example of one that actually you have a full page of it. That's an important slide, that one that has for the nonmetals and it shows the polyatomic ions. Most of them are cations. What I tell students is at the bottom I would write these. Ammonium is NH4 plus. Okay, so those 5 atoms run around with a +1 charge. And then this is one of my least favorite polyatomic ions. It's a cation, which is unusual. But not only that, but it's called the mercury 1 polyatomic cation. And so notice mercury 1 has 2 mercury atoms joined together with a collective +2 charge. So what I want you to do is think, whenever you see or have to use it, think of those 2 mercury atoms as basically covalently bonded, solid, bonded together. You cannot split that, all running around with a +2 charge. Near as I can tell, the reason they call it mercury 1 is because if you take +2, actually the oxidation number for each one of these is a +1 individually. But mercury 1 polyatomic cation is Hg2, 2+. Not my problem, now it's yours. Okay, so that's the polyatomic cation. And I have some hints about the polyatomic anions. Now, you're going to need to memorize the polyatomic anions, and I'll come around with these here in a minute. But these that I'm going to leave you with, basically you make them into flip cards, okay? Now, this one's pretty obvious. So you'll have this sheet. What you do is you cut here, and then you cut here. Like, for instance, you would fold this over. You'd see NH4 plus and ammonium on the other side. Those are kind of obvious. You'll get a set of these. And if you don't want to use them for that, they make great scratch paper. Okay? So these are pretty obvious, too. These are just the monoatomic cations. Let's see. 3rd page. What page? Okay. Finally, near the end, and maybe you'll just only want to use some of these, but this is it. That's what I try to tell you. So you need to memorize these polyatomic ions. Okay, these actually are listed on that last PowerPoint slide. You also have a full page of it. Okay, and that's what I told you to add. I think what's not listed are those 2 polyatomic cations. Okay, so that's how that works. So most of them have oxygen. The ones that don't have oxygen are cyanide, Cn minus. Okay, that's on there. So you need to memorize cyanide, Cn minus 1. Thiocyanate, SCN minus 1. Triiodide, I3 with a -1 charge. You cannot split those up. Okay. So some other ones, well, these are just, I mentioned cyanide and triiodide. Hydroxide is an important polyatomic ion, hydroxide. Now, the problem is, and I'll try to give you some ideas on how to combat this, but when you add oxygen to an atom and make it a polyatomic anion, you're going to end up with a lot of 8s and ites, or ites and 8s, okay? And I'm going to try to kind of help make sense of that. So in general, and the 2 examples I have up here are sulfur and nitrogen. These are 4 polyatomic anions, okay? Now, if we group them, we do see a trend. If you group the sulfur, you see a trend that ites always have fewer, okay, than 8s. Okay? Ites always have fewer oxygen than 8s. relatively speaking, with that particular atom. So we have sulfite, SO3 2 minus. We have sulfate, SO4 2 minus. Now, it took me a while, but the cool thing is they both have the same charge. You're like, yes. Okay, so that's good. Now, relatively speaking, because if we switch up and we switch gears from sulfur to nitrogen, again, we have two oxyanions, polyatomic anions. So we have an NO2 minus 1, okay, that has NO2 nitrite, has 2 oxygens. It has fewer than nitrate, has 3 oxygens. Don't blame me. It's just the way atoms kind of tend to do their thing, okay? A -1 charge for both of them. Relatively speaking, the nitrite has fewer oxygens than the nitrate. NO2 minus, NO3 minus. They both have the same charge. But it gets even better. The halogens go on a spree with regard to forming different polyatomic ions. The halogens, group 7A, okay, beginning with chlorine, basically they form 4 forms of oxygenated polyatomic anions. But they're a great pattern, okay? So you have, for instance, we have ClO, and they're all -1 charge. ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. Now, right dead in the middle, okay, we have your ites and ates. Right dead center, we have your ites and ates. And bromine would do this, and I can't remember what else would do it. Yeah, iodine would do it. I don't think fluorine does. Yeah. But right down in the center, we have less for ite, and we have more for ate. If you have even less than less, you have, like if you are really, really, really chilly, your temperature is really below, you're hypothermic. So we actually add a prefix. Now we have hypochlorite. Okay, if you have more than more, then we add the prefix per. So you have perchlorate. Okay, so the ite and ates will get you down the road, especially with regard to, I pulled out sulfur and nitrogen. It also works for phosphorus. We have a phosphite and a phosphate. That's my hints. There's a little bit more though. So some polyatomic ions that are -2 or -3 pick up a hydrogen, and in doing so, they kick back their negative charge 1. It's like adding a +1 to them. Okay, and I have some examples coming up here in a minute. Now, if you have a polyatomic ion with a hydrogen, the hydrogen needs to be part of its name. Okay, and I have some examples, I think. So, for instance, sulfur, okay, we knew we have sulfite, SO3 2 minus. You kick in a hydrogen, you got to include it in the name, so it's kind of got like a hyphenated last name. So hydrogen sulfite, instead of being 2 minus, it's 1 minus. Okay, sulfate, hydrogen sulfate. Some people know hydrogen sulfate and hydrogen sulfate as bisulfate and bisulfite and bisulfate respectively. That's fine. Carbonate, CO3 2 minus. There is no carbonite as far as I know. Maybe there is, but that's not one to memorize. CO3 2 minus. You can kick in 1 hydrogen, and it's hydrogen carbonate. Instead of being 2 minus, it's simply -1. Phosphate, PO4 3 minus. You can kick in 1 hydrogen, hydrogen phosphate. Now instead of 3 minus, it's 2 minus. Now this actually is one that sometimes students stumble over. If you go ahead and take your phosphate, and if you add 2 hydrogens to it, okay, that's part of the polyatomic ion. Man, this thing has, let's see, 2, 3, this thing has 7 atoms all running around with a -1 charge. Actually, it has a hyphenated the full name of the polyatomic ion is dihydrogen phosphate. Now, with that said, and I don't know how to warn you about this because some of you guys have done nomenclature of covalent compounds. This is all ionic compounds. And I have a hard time convincing students sometimes that the only place you will ever, notice how I'm getting very quiet, the only place you will ever use di is actually right here. You know, I'm not going to do naming covalent compounds this semester. This is the only place you're going to use di. Don't use it. Don't use it. Okay? Sometimes people want to use mono, tetra, you know, quint, you know, hepta. I don't know. Just don't do it. All right. So this is the last slide. Remember I told you to go ahead and down here at the bottom write NH4 plus ammonium, because I don't think it's on here. Also, nope. And then I said you write Hg2, 2 plus, my least favorite polyatomic ion. That is the mercury. I like the mercury program. Mercury 1. Okay. So let's take a look at that last section. Should work very similarly. Yeah, it's the longest section. 2 pages. But now here you need to remember all we talked about with the cations and the crisscrossing and all right, let's see. Let's pick on I. See if I can get it right this time, the first time. All right, I got barium, Ba2 plus, and BrO4 minus. Now, you're like, oh my gosh, I know that's bromine, and it's got a lot of oxygen. Actually, the maximum oxygen is 4. So it's going to have an 8, and we're going to do the per in front of it. So actually, this is per bromate. Okay, per bromate. That's BrO4 minus. So let's crisscross. Okay, so the number of bariums I need, I'm thinking 1. Okay, sometimes students, I know, do you have to put a 1 there? Well, not usually, but I'm going to put a 1 there just for kicks. Now, the number of BrO4 minuses per bromates I'm going to need actually is 2. So in this case, I am going to have to put parentheses, BrO4, okay, 2 outside of there when I crisscross. You can leave the 1 there. I would. Now, when I name this, if you're like me, barium, now don't be shy about finding a periodic table and locating barium on the periodic table. Because we know if barium is it actually is in 2A. And if it's in 2A, then we do not use Roman numerals in its name. And if you want to get this one fully correct, that's the route you're going to have to go. So the first name is barium, no Roman numerals, and the last name is per bromate. Now, do not blow, well, I guess you can. I would not blow off this topic of nomenclature for ionic compounds. I already told you your unit exam is going to be a 5th to a 4th of this very stuff. And this is the only place we're going to hit it hard. Let's look at dun, 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 dun. I think you guys should be okay with those. Don't forget that last section you have to write the component ions and then crisscross. So I'm just going to kind of leave you to it.